Hello, everyone. Welcome back. Today is January 1st, 2025. I wish everyone a happy new year. Today, we're going to talk about lecture 8 on Gibbs-Duhem equation in homogeneous equilibrium systems. A typical approach to derive Gibbs-Duhem equation is through the following procedure. First, let us consider homogeneous system. Because homogeneous, we can normalize its molar quantities. Here we show Sm, the molar entropy equal to S divided by N, molar volume, V divided by N, mole fraction, and I divided by N. Then we consider a small portion of the system as a subsystem. So this is shown by this blue circle here. And then the total energy change of the system it's du subsystem of is du equal to TdS minus PdV plus summation of mu I dni for component I. Then we expand the subsystem by dn. Then the change of entropy of the system subsystem is ds equal to Sm dn. The volume change dV equal to Vm times dn. And the change of a component I is dni equal to xi dn because it's homogeneous. So the change of the internal energy of the subsystem is TSM minus PVM plus summation each component for all component mu I xi times together times dn. Then we can, because homogeneous, we can do integration because the whole system in the STSM, PVM, mu I xi, they are not changing. They are homogeneous in the system. So simply times the n of the number of moles of system give us the internal energy of the system. Then we move n inside to the parentheses, then become Ts PV plus mu I dni. So, we all learn this one. When I was an undergrad student at Central South University in China, we learned this one too. However, I always had an issue for this one. It's because we typically think about ds, dv, and dni, they are independent. However, in this procedure, this approach, they're not independent. Okay. So then I thought maybe we can derive it in a way. So consider them as three exchanges independent. So I follow what Mazhila usually do in his class is to do the virtual experiment. So I call it a virtual experiment approach, which means is that we consider subsystem again in the whole system. This is the blue circle here. We consider only hydrostatic pressure, dW equal to minus PdV. We consider it's dW equal to 0, dQ equal to 0, so dV equal to 0 between the subsystem and the system. Then we add one component, dni, into the subsystem. So we know that the change of internal energy of the subsystem equals to ui dni, with ui is the partial internal energy of component I. However, I also know that this component dni also has a volume, which is vi dni. So that means the subsystem volume we have to increase. Okay. And however, we say the volume is constant. So it keeps the volume constant. That's our condition, right? Because we only want to change the mass as the independent process. So that means the pressure of the subsystem will increase because dV is fixed. However, the system must be still equilibrium after this internal process. That means the pressure must be the same because the pressure is the potential has to be homogeneous. To maintain the pressure homogeneous, the subsystem has to expand a little bit, right? To release the pressure. So increase the volume, divided by to decrease the pressure. So the subsystem doesn't work to the rest of the system. So the work is done pressure is fixed from outside of the subsystem. The volume change, the VI dNI, is a minus sign because the volume expansion of the subsystem will lose some energy. Okay, that work to the surroundings, which is the rest of the system. So the du change of the subsystem would be now has two terms. The first term is the addition of the internal energy due to the component, is the ui dNI, and minus the work the subsystem does to the rest of the system, which is minus the PVI dNI. And then remember we defined the mu I. So mu I is equal to ui minus TSI. So we have the plus TSI back here. So now we have TSI dNI, then plus mu I dNI. Now we have mu, the chemical potential of the component, I is equal to ui minus TSI. Then we have the work the subsystem does to its surroundings, which is the rest of the system. So it's minus the PVI dNI. So we move the dNI out and combine, now the equation becomes TSI plus mu I minus the PVI. So the partial entropy, chemical potential, which is defined as ui minus TSI, and the partial volume of the component I. Now, because systems are homogeneous, okay, we also add each component individually, but proportionally, so to maintain the same composition everywhere in the system. So then dNI, xi dm, and du, now simply you have xi times dm, so you put in each component. So TSI times xi, mu I times xi, minus PVI times xi. Now again, because the system is homogeneous, so we do simple integration, the summation from the small subsystems all the way to the whole system. So now we get a U equal to TS because TSI xi times dm ni, so it becomes TS of the whole system, and minus the PV of the system plus the chemical potential of mu I ni of each component, or component I. So this equation is the same equation as we derived from the typical conventional approach. But at this time, we only consider one independent exchange between the subsystem and the rest of the system, which is Ni. Then we added the individual components one at a time, think about, and put them together, we get some equation. Because during this process to maintain equilibrium, and the system does some work, subsystem does some work to its surroundings with the rest of the system. So this virtual experiment approach, I avoid the issue I had, which is that the three independent process exchange, they must be independent. Okay, now after we get this equation, then we can derive the Gibbs-Duhem equation. Now we derive the U equal to TS minus the PV plus the chemical potential of each component summed together. And we define the Gibbs energy, by definition, is U minus TS plus PV. So TS cancel each other, PV cancel each other, we have one term left, one summation left, which is the chemical potential, mu I Ni summation. Then we do the differential, differentiate this equation. Differentiate the equation gives us the dg. Now we have two terms. So it's dNi, the first differential of the Ni, and then the differential of the mu I, chemical potential, we get two terms. But we also know that from the combined law, dg equal to minus SDT minus Vd minus B plus summation mu I dNi. These two dg must be the same. So we subtract these two dg equations. The left side, dg minus dg equal to 0. You have the Ni d mu I as one left. And then this is all from change from negative to positive, but plus SDT plus Vd minus P equal to 0. Okay. So we know this is molar quantity, this is potential. So molar quantity potential, we can write a compact form, which is the summation of XA dYA equals 0. So it's the molar quantity and it's conjugate potential, differential. Sum together equals 0. So it means that the potentials are not independent in a homogeneous equilibrium system. This is very significant because it will be we'll use this one to derive the Gibbs phase rule when we have a non-heterogeneous equilibrium, non-homogeneous equilibrium systems. All right, thank you very much. And I wish everybody all the best in the new year.